Alright, in this project we will build a reinforced learning system that can adjust machining parameters in a CNC process. What does that mean? It means the agent will learn how to choose spindle speed, feed rate, and depth of cut in a way that balances productivity, surface quality, tool wear, and safety. We will set up a custom environment that simulates how these variables affect forces, temperature, roughness, and tool life. So instead of manually tuning parameters or relying on fixed rules, the system will gradually figure out good operating ranges through trial and feedback. Later, we'll train a soft actor critic agent on this environment. The agent will try actions, observe the results, and update its policy to improve performance. And once the training is done, we will also test the model in evaluation modes and finally use it in real time optimization setup where it will suggest safe parameter adjustments based on current machining conditions. So let's begin. And here you can see our libraries: torch, numpy, random math, matplotlib, collections, etc. Okay, and look at here, we are defining a CNC environment that will act like our virtual machining system. The very first thing inside the class is the initialization method, and here we are setting the ranges from different variables. For example, the maximum tool wear is set to 0.3 millimeters. The maximum surface roughness is 5 micrometers. The maximum cutting force is 1000 newtons. The maximum spindle load is 100%, and the maximum temperature is 200 degrees Celsius. These are the outer safety limits of the machine. Then right after that we see the bounds for the controllable parameters, and spindle speed can vary between 500 and 8000 revolutions per minute. The feed rate is allowed between 20 and 500 millimeters per minute, and the depth of cut can move between 0.1 and 3 millimeters. And what we are doing here is simply telling the environment what is physically possible and what is not. That's okay. And below those limits we also defining some starting values. Okay, and what are they? The spindle speed is initialized to 2000 rpm, feed rate starts at 100 millimeters per minute, and the depth of cut is 1 millimeter. Along with that, we track the state variables that will change step by step, and tool wear begins at 0.05 millimeters, surface roughness at 1.2 micrometers, cutting force at 300 newtons, spindle load at 60%, and temperature at 80 degrees Celsius. There is also a step counter that starts at 0 and goes up to 1000, which is the maximum steps allowed in a simulation episode. Then there is a smoothing factor called beta set to 0.2, meaning parameter changes won't jump immediately to the new values, they will be applied gradually. And finally, some thermal dynamics parameters are set, and what are they? Ambient temperature at 30 degrees, a time constant of 40 steps, a reduced heat generation coefficient, and a cooling factor. Together, these define how the machine heats up and cools down during operation. So overall, this initialization part sets the stage, it fixes the physical bounds, defines initial conditions, and prepares the environment to behave in a realistic way before training even starts. Let's talk about reset function. When we call reset, the environment goes back to a fresh state with some randomization. For instance, tool wear is set to 0.05 plus a small random noise. Surface roughness is 1.2 plus noise. cutting force is 300 plus some variation, and so on for spindle load and temperature. The spindle speed, feed rate, and depth of cut are also randomized around their base values, but still clipped to remain within the safe ranges we said earlier. Why we do this, and why do we do this? Because it prevents the agent from overfitting to one specific starting condition. Okay. Every episode begins a bit differently, so the agent learns a more robust policy. At the end of reset, the function returns the current state, which is normalized. And at that, normalization happens inside the get state function, and here each value like tool wear, roughness, cutting force, load, and temperature is divided by its maximum limit. For example, tool wear divided by max tool wear, or surface roughness divided by max surface roughness. And the spindle speed, feed rate, and depth of cut are also divided by their own maximum values. This way, all state variables end up scaled between 0 and 1. This makes it easier for the neural networks to process them, because the inputs have consistent ranges instead of raw engineering units. That's why this function is so important. It translates physical measurements into a normalized state vector that the agent can understand and use for decision making. And let's look at how actions are handled. Okay, this part is done. The squash to range function maps an action value from the -1 to 1 into the real world parameter range. So if the action is -1, the parameter becomes the minimum value. If it is +1, it becomes the maximum value, and values in between are scaled accordingly. And this is how the continuous actions from the agent are turned into spindle speeds, feed rates, and depth of cut values that the machine can use. After that, there is a project save function. This one is interesting. It acts as a safety layer. What it does is check if the chosen speed, feed, and depth values might cause unsafe conditions like too high cutting force, too much spindle load, or too much temperature. If the estimated force is above 800 newtons, or the load above 100%, or the temperature above 175 degrees, the function adjusts the values back toward safer regions. It repeats this checkup to 12 times until the parameters are acceptable. This way, even if the policy suggests something risky, the projection pulls it back to the safe levels before applying it. That is okay, and here we come to the step function. This is the main loop of the environment. When an action is received, it first converts it into actual machine set points using squash to range. Then, instead of jumping directly to those set points, it applies some smoothing with the beta factor. For example, the new spindle speed is calculated as 0.8 times the current spindle speed plus 0.2 times the target spindle speed. And the same applies for feed rate and depth of cut. This prevents unrealistic jumps in machine parameters. After updating the parameters, the environment calls the update state function to recalculate tool wear, surface roughness, cutting force, load, and temperature. It then computes the reward and checks whether the episode should end. The conditions for termination are reaching the maximum number of steps, tool wear exceeding its limit, temperature going above 178 degrees, or surface roughness exceeding 4 micrometers. At the end, the function returns the next state, the reward a flag for whether the episode is done, and empty dictionary for compatibility. Okay. Let's go into update state. This function it simulates what happens physically after applying the new parameters. The first calculation is the material removal rate given as spindle speed times feed rate times depth of cut divided by 1 million. Then tool wear increases by a rate that depends on spindle speed and feed rate. Surface roughness is estimated as 0.8 plus 0.5 times feed rate over 100 plus 2 times tool wear with some random noise. And cutting force is calculated using a base factor times depth of cut times feed rate multiplied by a wear factor that grows with tool wear. The spindle load is estimated as 20 plus 0.03 times cutting force plus 0.002 times spindle speed, again with noise and clipped between 0 and 100%. And lastly, temperature is updated using a thermal model, and it accounts for cooling back toward ambient and additional heat from the interaction of speed force. There is also some noise added to keep it realistic. After these updates, the machine state is clipped so it doesn't exceed physical limits. So with each step, the environment mimics the real process. The tool wears down, the surface gets rougher, forces the loads change, and the temperature rises or falls depending on the machine conditions. Okay, and I hope that is okay, and reward function is here, and okay, so let's see what's happening here. Reward, calculate reward, and okay, so this is where we define how good or bad a particular machining step is. So what are we doing here? We are translating the physical results, things like material removal rate, surface roughness, tool wear, and temperature, into a single numerical score that the reinforcement learning agent can use to improve its decisions. Without this, the agent would not know whether its actions are helping or hurting the machining process. We start with some reference values, and what are they? The target surface roughness is set to 1.2 micrometers, and anything up to 2 micrometer is considered acceptable. For spindle load, the maximum safe value is 85%, cutting force is limited to 800 newtons, and temperature should ideally stay below 150 degrees Celsius. These numbers basically set the tolerance window for quality and safety. That's okay, and then we calculate the productivity reward, and here we use the material removal rate, which is spindle speed times feed rate times depth of cut divided by 1 million. Instead of using this directly, we take the logarithm written as log 1 plus MRR, that is log base E 1 plus MRR, okay, and multiply it by 2, okay. This scaling makes the reward grow with productivity but prevents it from exploding when MRR is very large. And quality reward is here. If the surface roughness is less than or equal to the target, the agent gets a full bonus of +1. If it is worse than the target, then we apply a penalty that grows quadratically as the roughness increases away from the limit. This way, the closer the agent stays to the desired finish, the better it is rewarded. Okay, this part, okay, and we also penalize tool wear. The wear ratio is calculated as tool wear divided by maximum tool wear. If this ratio goes above 70%, the penalty grows exponentially, specifically as -2 times wear ratio to the power of 4. Below 70%, the penalty is gentler, minus 0.4 times wear ratio squared. Okay, on top of this, there is also another penalty to reflect tool replacement cost, minus 3 times wear ratio cubed. So, well, the more the tool wears, the more the agent gets punished economically. Okay, I'm looking for temperature. We set an optimal band around 110 degrees Celsius with a tolerance span of 50 degrees. The reward is calculated as minus 0.8 times the squared deviation from that. Failed to connect, but anyway, it doesn't matter. Okay, what I'm saying here, the reward is calculated as minus 0.8 times the squared deviation from that center divided by the span, and this encourages the agent to keep the cutting temperature in a reasonable band. Too cold or too hot both give penalties. That is okay. And there is also a penalty for too low feed rates. If the feed is below 80 millimeters per minute, we compute the difference from 80 divided by 80 and square it. The penalty is then minus 0.8 times that squared value. This reflects the minimum chip thickness effect, where very low feeds hurt efficiency. Spindle load is here. We define a target band between 60 and 75%. The normalized load is spindle load divided by its maximum, and then we apply a penalty if it drifts away from the center point of 0.68 against squared and scaled. This keeps the machine working in its most efficient region. And on top of this, we include explicit safety penalties if the temperature, cutting force, or spindle load exceed their maximums. We calculate how much they overshoot as a fraction of the limit. Then we apply penalties: minus 3 times our temperature, minus 1.5 times our force, and minus 1 times our load. This acts like a hard pushback against unsafe operating conditions. And finally, there is a small survival bonus of plus 0.05 added each step. The idea is to encourage the agent to keep the episode going without hitting termination conditions too early. That is okay, and let's look at this class actor. And let's see what's happening. Why it doesn't work? Sorry. And yes, okay, let's stop here. And I think that is because of this failed to connect. Anyway, let's go. Turn to the policy and value networks, and starting with the actor class. This is a neural network that outputs actions. It takes the current state as input and passes it through 3 hidden layers of size 256, each with value activation. Then it splits into 2 heads, one for the mean of the action distribution and one for the log standard deviation. The log standard deviation is clipped between minus 20 and plus 2 to keep it in a stable range. And the forward function returns these 2 outputs. The sample function is more involved. It uses the reparameterization trick. B draw from a normal distribution with the given mean and standard deviation, then pass the result through a hyperbolic tangent function tan h to squeeze it into range from -1 plus 1. That is important because our actions need to map back into the spindle speed, feed rate, and depth ranges. We also compute the log probability of the action with a correction term for the tan-H transformation. And this probability is later used when training the agent with entropy regularization. And class critique. This is the value function approximator, and it actually uses twin Q networks. Each Q network takes as input the state concatenated with the action, passes it through two hidden layers of size 256 with value activations, and output a single scalar Q value. The forward function simply returns the results from both networks. Having two critics reduces our estimation bias, since during updates we always use the smaller of the two Q values. And we have the replay buffer. This is the memory module that stores past experiences. Each entry contains a state, the action taken, the reward received, the next state, and a flag for whether the episode ended. And the buffer has a maximum size of 100,000 transitions. We can sample random mini batches from it for training, which breaks the correlation between sequential steps and stabilizes learning. We get to the SAC agent class, soft actor critic. This is the main controller that ties everything together. During initialization, it sets up the actor, the critic, and target critic network. The parameters of the target critic are copied from the critic at the start. It also sets up optimizers, Adam in this case, for both the actor and critic. For entropy tuning, we have two options. If auto entropy tuning is enabled, we set the target entropy to minus the dimension of the action space. We also introduce a learnable parameter called log alpha, okay, and update it using its own optimizer. And alpha is then calculated as the exponential of log alpha. If auto tuning is disabled, alpha is fixed to 0.2. We also define the key parameters: gamma for the discount factor, tau for the soft target update rate, and the replay buffer. Okay, then we come to the select action function. Given a state, we pass it through the actor network. If we are in evaluation mode, we simply take the tan-H of the mean. Otherwise, we sample stochastically from the policy distribution. If requested, we can also return the log standard deviation as a measure of uncertainty. The action is finally returned as a NumPy array. You can see. So what we have seen here is the backbone of the soft actor critic algorithm. And I hope that is okay. And let's look at this update function. What we are looking at here is the training and evaluation loop together with the real-time optimization part. So why are we doing this? Up to this point, we have built the environment, the reward function, and the soft actor critic agent. Now we need to actually train that agent, monitor how it performs, and later deploy it in a safe real-time setting. We begin with the update function. This function draws a batch of samples from the replay buffer and updates both the critic and the actor networks. First, the states, actions, rewards, next states, and then flags are converted into PyTorch tensors and moved to correct device, either CPU or GPU. Okay, that is okay. Then for the critic update, we compute the target Q values. These come from the target critic network applied to the next state and next action. The formula is target Q equals reward plus gamma times target Q adjusted with entropy regularization. Then we compare the critic's current predictions with these targets using mean squared error, backpropagate the loss, and update the critic weights. After that, we move on to the actor update, and let's switch. That is here, and the actor's goal is to maximize the expected Q value minus the entropy penalty, so the loss includes alpha times log probability minus the Q estimate. That gets back propagated and the actor parameters are updated. If entropy tuning is enabled, alpha itself is updated too, to keep the policy sufficiently exploratory. And finally, we do a soft update of the target critic network with tau, blending its weights with the current critic weights for stability. That's the learning cycle: sample, update critics, update actor, adjust alpha, and update targets. Now, CNC optimizer class, and this is the high-level controller that runs the training loop. It initializes an environment and an SAC, soft actor critic agent with state dimension 8 and action dimension 3. The tree method starts by printing a header so we know what's happening, and then runs for a chosen number of episodes. Inside each episode, we reset the environment and keep track of the cumulative reward. Then, step by step, we let the agent select an action, apply it to the environment, and store experience into replay buffer. Okay, and once the buffer has more than 3000 samples, the agent starts updating its networks using the function we just explained. And that is true. And after the episode ends, we log the total reward. Every 100 episodes, we print the average return over the last 100 runs, along with the final parameters and state values like tool wear, surface roughness, temperature, and load. That way we can monitor how the agent is improving over time. That is okay. Moving to evaluation. The evaluate method runs a fixed number of episodes but with deterministic actions. That means instead of sampling from the distribution, we take the mean action directly. The purpose here is to check how well the agent performs when it is not exploring anymore. For each evaluation episode, we record the total reward and also print out the final parameters and state variables. At the end, we compute the average evaluation reward, which gives us a clear picture of trained policy's performance. And now comes one of the most interesting parts, the real-time optimization method. This is where the agent can be applied to live machining conditions. First, the current state values such as tool wear, surface roughness, force, load, and temperature are normalized using their maximum limits. Then these values are updated into the environment so the projection layer can apply safety checks. The agent then selects an action and we convert that normalized action back into absolute values for spindle speed, feed rate, and depth of cut. Before applying them, we run the project safe function to make sure they won't break any constraints. Okay. On top of that, we measure uncertainty by looking at the variance of the policy. If uncertainty is high, we blend the new recommendation with current parameters, effectively playing it safe. And finally, the function returns a dictionary containing the recommended parameters, the confidence level, the policy's uncertainty, and whether a conservative blend was applied. This makes the optimization usable in a real CNC setting where safety and reliability are critical. Okay. And for visualization, we have some functions you can see. At main execution, if name main parent CNC machine RL optimizer and optimizer EQ CNC optimizer and other things. And I wanna look at our outputs now. So that begins here. Okay. This is where we see how the training evolved across episodes and what kind of results the agent ended up producing. So why are we doing this part? Because building and coding the environment and the agent is one thing, but unless we evaluate the training curves and the numerical logs, we can't say if the system is really working. At the very beginning, episode 0, the average return was about negative 545. That tells us the agent was performing poorly at the start, which is completely normal. The final parameters at that point were spindle speed around 3900 RPM, feet about 300 millimeters per minute, and depth a little above 1 millimeter. The state values showed tool wear already at the maximum limit, surface roughness around 2.8 micrometers, and temperature fairly low at 63 degrees Celsius. What's also interesting is the entropy coefficient. Alpha was at 1.0, which means the policy was exploring heavily. That's okay. If we jump ahead to episode 100, the average return improved to about negative 146. By this point, spindle speed increased to 5400 RPM, feet dropped to around 160 millimeters per minute, and depth of cut was higher at 2.69 millimeters. Surface roughness is improved to 2.2 micrometers, and temperature rose to 85 degrees Celsius. Alpha also decreased to 0.097, which means the exploration was already getting smaller. 200 by by episode 200, the average return was around negative 40, which shows the agent was learning to avoid the heavy penalties. Spindle speed was now close to 7000 RPM. Tool wear stayed stable and temperature climbed just below 100 degrees. As we keep going, the values stabilize further. Around episode 300, the average return turned positive, about 38, and by episode 500, the return was consistently near 47. From that point onward, the parameters settled around 7800 RPM for spindle speed, feed rates between 140 and 170 millimeters per minute, and depths around 2.7 millimeters. Surface roughness was consistently near to 0.1 to 2.3 micrometers, which is close to the target quality, and temperature rose above 100 degrees but remained below the safety cutoff. And let's look at our plots. What do the plots show? The training progress graph has reward on the vertical axis and episode number on the horizontal. Early on, the curve is very noisy and stays negative, but after about 200 episodes, it crosses into positive territory. The red line, which is the moving average, shows a steady climb until it stabilizes around 50 reward. The second plot shows the last 200 episodes in detail, and you can see fluctuations from episode to episode, but the values remain consistently positive, generally between 40 and 60, with occasional peaks near 80. That variability is normal in reinforcement learning. At the evaluation phase, we can see that the trained agent performs even more consistently. Across 5 evaluation episodes, the return ranged from about 40, 90 to 62, averaging at 56. Okay, and the final states all show tool wear hovering around 0.3 millimeters, which is right at the threshold surface roughness near to 0.1 micrometers and temperatures in range of 108 to 109 degrees Celsius. And these values indicate that the agent has learned to balance productivity and quality without violating safety constraints. Finally, the real-time optimization example gives us a sense of deployment. The current state has tool wear at 0.15 millimeters, which is half the limit, surface roughness at 2.5 micrometers, and temperature at 170 degrees Celsius. The agent recommends a spindle speed of about what is that? A spindle speed of about 7,700 RPM, a feed rate near 126 millimeters per minute, and a depth of cut of 2.9 millimeters. It also provides confidence at 0.739 and policy uncertainty at 0.35. That means the system is reasonably confident in its suggestion while still being cautious.